Welcome to this new series of white paper videos. Today we'll be talking about Facebook Memcached. As you can expect, Facebook is a very large company. Instagram is owned by them, WhatsApp is owned by them. They have a lot of data and a lot of it has to be cached. Way back in 2010, Facebook had a very specific use case for Memcached to render their home page or in general their pages quickly. And why is this a challenge? Because when you're trying to get a home page, even on Instagram, when you're trying to get your profile page, there's a lot of stuff which happens in the background. Just imagine Brad Pitt has a post. You want to see the funniest top comment, the meme, the joke there. So you come here. Then you want to see what have people replied to that top comment. So you come over here. You get to see the number of replies. You can load more if you want. A lot of this stuff, ideally, you want to cache. Even if you don't get this all together in the home page, you want to keep them ready. You want to keep them in cache. And so this entire tree has to be cached per user. So this is a very difficult problem to solve for many reasons. One is the amount of data is large, but even more importantly, this is no longer a single query. It's no longer a key value pair query that you're doing. To get a single home page, you are getting multiple key value pairs. So this becomes a branching kind of operation where you spread out, hit multiple machines. This posts can be a separate service on Facebook being managed by, let's say, 10 engineers. Notifications is a service in Facebook. Messages is a service in Facebook. Each of these services are being hit. Posts internally may have multiple services. It might be that you get a recommendation service which just tells you what should you see on your homepage. You may also have something which is just activity, the number of likes, the type of likes, the comments on every post. So you see that the work of maybe dozens of engineers is being hit every time you are trying to get your homepage. And all of these engineers want to use a common cache so that they can get responses quickly. This is the primary challenge we'll be talking about today. It's discussed in detail in a white paper, Scaling Memcached at Facebook. We're going to take the gist of that paper and describe it today here. I've also taken stuff from different talks, some by Mark Zuckerberg, some by different Facebook engineers to explain Memcached in detail. So put yourself in Facebook's shoes. This is 2010. You are the staff engineer at Facebook, or you are one of the staff engineers at Facebook. You get together, you decide that a lot of engineers are doing the same thing. They need a common cache. If we could build that, then our engineering team would move faster. So the first thing you want to do is you want to create a cache which is used by all engineers or most engineers at Facebook. The second thing you want to do is, of course, take care of this use case. This is the thing which is motivating you right now, making hundreds of concurrent / parallel key value reads per query. A single person asks for a home page, you get hundreds of data points. The third thing that you want to do is have low latency. There's really no point of having a cache with high latency. So within 10 milliseconds is ideal. And the final thing which is discussed in almost every system design interview is where do you lie in the CAP theorem? Okay, let's discuss this for a while. Let's try to break some myths here today. There's a CAP theorem thing of you can either be perfectly consistent or perfectly available as long as you want partition tolerance. So if you're building a distributed system, a distributed cache at Facebook, then you can choose consistency or availability. Memcached is neither. Okay. When it comes to trade-offs, in some cases it chooses consistency. In some cases, it chooses availability. As an engineer, this is something that you should know, and I see this happening a lot, even in team discussions, design meetings. People talk about, should it be perfectly consistent or perfectly available? That's, I think, the wrong question to ask. Depending on your requirement, depending on what you want your cache to do, look at whether this use case calls for consistency or this use case calls for availability. At a high level, though, when it comes to Memcached, Facebook suggests that they will go for a higher availability system, eventually consistent. Okay, so very high availability is what they're looking for. That does not mean perfect availability. They also try to make the system as consistent as possible. Why is that? because a cache which gives you stale replies does not look like a nice social media system. If on Instagram your friend has replied to a post and you're scrolling and you don't see the reply, that could potentially change the way that you are responding to that post. Remember that this cache is going to be used by hundreds of engineers, so you don't want to handicap yourself by limiting yourself to high availability. Okay, this is a philosophical choice. What can you do to make the system be used by many engineers at Facebook? That's the first question we'll answer. This is a people problem. It's interesting to think of. It's like a product problem for engineers. You're building an engineering product for engineers. In general, if you're looking to get promoted to staff or senior staff positions, what you want to do is you want to build systems which have tremendous impact in the organization or outside the organization. Basically, you make more money or you save money for the organization. As an engineer, you're looking most of the times to save money. How do you do this? If every engineer in your org is going to create their own cache, that is going to cost the org. It's going to cost Facebook a lot of money in terms of development, maintenance, testing, and just deployments. So what you want to do is you want to create a caching system which is used by everybody. So you want high adoption rates. How do you do this? This is your primary metric as an engineer. Everybody should use your system. Well, one thing that is suggested by many people is to do good documentation. Another thing which is suggested is do good error handling. Another part which is not really technical but whatever is soft skills. You make strong connections, you let people know, you understand what the requirements are. But one thing that you really should focus on, which comes from the side as a big thing, is the ease of use. Okay, if you're building a system and it's easy to use, you'll see that onboarding onto the system is quite easy. Of course, one thing that I should mention is you have to meet all the requirements or most of the requirements of the engineers. If you're not going to meet the requirements, there's no point in them switching to your new solution of a cache. But we are going to talk about ease of use here. And one way that you can do this is whenever a person is connecting to your system, they are going to be connecting using APIs. For making that request, you have to create objects, you have to hit their API, you have to read the documentation. Can we make it easier? If you instead give them some sort of code, let's say the engineers are writing in Python, you give them a client library which they can import into their system, let's say hash include, or in Java you would have an import statement on top. You would give them this library, their code would be able to compile the library. The library would have an HTTP client. It would construct objects for them. As long as they pass in the parameters, it would be like a function call. They would just send the parameters, not create a request object. And when the response comes from your API, the object will be constructed. You have already taken care of 3 steps for them now. Who's writing these libraries? Who's writing the Go library? Who's writing the Python library? The engineers in Memcache. They are taking the effort. Apart from this, if you give them a client library, the API contract gets updated automatically. They just need to update the client library version and things work smoothly. This increases adoption rate. Makes life easy because engineers, like everybody else, are lazy. So this was an interesting point of Facebook. Apart from this, also there's a few things that the client library does. Like I mentioned, there is compression. So if you're trying to compress a bunch of values, or if you're trying to send requests in batch, this will be taken care of by the client library. This is especially useful, sending requests in batch, because you are making a homepage request or a profile request. You need to get multiple keys. We talked about the homepage having the number of messages, the number of notifications, the number of posts, the number of likes in those posts, all of that stuff, all of those data points have to be hit. With a client library, you can batch those requests. You can put those requests together, make a single request to Memcache with all of those keys, and when you get a response, you get all the responses together. So the number of requests you're sending is reduced, bandwidth is saved, compute is saved, and it just makes your process more efficient. So your services are happy with all the intelligence that you have on the client, and like I said, adoption therefore goes up. Now let's see how these API calls are actually made by the client. So if you're doing a GET request, a cache has a GET or a SET. First one is GET. When it comes to your web server, let's say you're trying to fetch the number of friends that Gaurav has. Okay, so it comes here. Then you call the cache. You say, get me all the friends of Gaurav. So that is a GET request. It's going to give you nothing because the cache is initially empty. You're then going to go as a web server when you get nothing back, when you get a null response. You go to the database. In this case, it is MySQL because we are talking about Facebook. MySQL then gives you a response. Number of friends Gaurav has is, let's say, 20. And this response is then populated into the cache. So you're going to say set the number of friends for Gaurav as equal to 20. If you're expecting the value to be in cache, then it is your responsibility to actually populate the cache. This is called a look-aside cache. Meaning that the cache is separate from the database and the person who's managing the cache is actually the web server. As an engineer, you don't want to manage this yourself. You don't want to ask for the number of friends and then if you get a response, then you do something. If you don't get a response, you do something else. So instead, to make things easy, this is managed by the client that we were talking about. When you call the client with a GET request, it's going to do this in the background and eventually just give you a response. Okay. The other operation you can do is set. Here, you are putting a value in cache, you're setting a value in cache. So someone just got added to Gaurav's friend list. You want to update the number of friends he has. Okay, you come to the web server, you say, look, let's update the value first in DB. Okay, so the green line shows what's happening when it comes to a write operation. And number one is update. Once the database is updated and you get a response success, you will now go and delete that entry for that key in the cache. So instead of updating the cache, you're actually deleting entries when they are being updated in the database. Why is this good? Because this is an idempotent operation. So in case this API call fails, you try to delete the value again and again. It doesn't really matter because you're just going to delete one key from cache, which can always be populated from database. If you didn't do that, if you said that instead set Gaurav's friends values to 21, then if the API call failed, you would have to manage the retries. And if you have to manage retries, there may be concurrent updates happening. So you don't take that headache. It's a very simple architecture, a look-aside cache, which is idempotent. Facebook mentioned it in their tech talk actually, which is using UDP to make GET requests, but using TCP to make SET requests. If you use TCP, the benefit is for every request that you make, you get an acknowledgement. So you send request number 1, you get an acknowledgement, you wait for it, and then you send request number 2. You wait for the acknowledgement, send request number 3. The benefit of this is the requests are serialized. If you're making SET requests, set the value of key 1 to 1, then set the value of key 1 to 2, you will see the final output as 2 because the SET requests are going in order. You're waiting for the response to come back before you make a newer request. But if you use UDP, you're really not waiting for a response. You say set the value of key 1 to 1. Before the response can come back, before you're sure that the request has actually reached them or it has been processed, you say set the value of key 1 to 2. So the final state can be anything. It's possible that the server gets this request first because of some network issues, maybe the first request failed, or it gets this request but it takes time to process it. For some reason it's pushed back in the queue. Whatever be the case, it's possible that this request is processed before this one. So the initial value is set to 2 and then key is set when this is processed to 1. So the final state is going to be k1 equal to 1 and you're going to lose this write. In the case of Facebook, that won't happen because you are now making SET requests using TCP. What about GET requests? You're using UDP. So if you say get me the value of k1 at timestamp 1, t1, and get me the value of K1 at timestamp T2, where T2 is greater than T1, what guarantee can you give in terms of responses? Nothing. You have no guarantee that the value that you will get at timestamp T2 will be a later value than T1. It's possible that this request gets a more fresh value of key1 than this one, okay, because of the same idea of processing out of order. What do they do if they get an anomaly like this, if they get responses out of order? They just drop the packets. If the packets are out of order, then Facebook, the client, treats it like an error. Okay, so 20% of all errors in Memcache is actually just out of order packet processing. In the case of Facebook, this is a worthwhile trade-off because they save 20% in request latency for GET requests. Now, what's powering this 20% reduction in latency? Mark Zuckerberg mentions that you don't need to create connections in UDP. So that saves on memory. You can basically have more keys in the same cache server as compared to earlier. So the hit rate is higher in the cache. The second thing is you don't have a limit to the number of keys you can fetch in a cache. If you look at file descriptors, then that's something like 65,000 per server. Facebook had updated this. The number of connections that a cache could host was more than 1 million. So they went in the Unix kernel and made those changes. But eventually they said that, we don't really need GET requests to go through TCP. Let's just use UDP. And the final benefit here is that you don't have head of line blocking. If you know about HTTP 3.0, it uses QUIC, which is basically UDP as a protocol. The reason why HTTP has also moved to UDP is because you don't want a single request to go to the cache and then make everybody else wait. Let's say you have 100 requests in a line. The first request is taking time. When it takes time, the rest of the 100 requests also wait in line. If they can all go in parallel, like in UDP, then you don't have any line blocking. So this problem of head of line blocking, you can imagine yourself to be in an airport and the person at the start is taking a long time to finish their counter query and you are here with your luggage, your flight might get missed. That's not going to happen. There's going to be no head of line blocking. You will have all requests going in parallel. So the savings are worth it. And the one thing you want to take away from this paper is the way that Facebook has scaled Memcache. The title of the paper is also Scaling Memcache at Facebook. And after seeing this, you'll really feel like, wow, the engineers there, the nuanced approach, the way that they looked at how users are using their system is outstanding. So pay attention, please. Facebook said, I need to scale my cache servers. I can only vertically scale to a point. I can't manage Facebook with a single node. So I'll have to horizontally scale eventually. How do you want to scale out? Do you want to shard your nodes? You want to shard keys into different nodes? If you do this, then for a key range of, let's say, 1 to 1000 and 3 nodes, you're going to have key range 1 to key 333 served here, key 334 to 666 served here, and key 667 to key 1000 served here. And as you add more nodes, you're going to be taking the keys from some of these nodes and populating the other cache. Okay, that's how you're going to distribute your load. The benefit of this is if a client has to fetch any kind of data, it knows exactly where that point data exists. The second thing is you can have more unique keys in your cache server. Just imagine that you have key values from key 1 to 1000. It's not that all 333 keys can be kept in a single cache server. So you're probably going to have 100 commonly used keys in this range being stored here. Okay, so each server can store 100 keys. It's serving a range of 333, but the top 100 are kept in cache. Similarly, here you have 100 keys, and here you have 100 keys. So out of a total of 1000 total keys, you can serve 300 through your caching system. All of the keys are unique. So we should go for sharding, right? Remember the access pattern, the way in which your data is being used by users. What are people asking for? they're asking for hundreds of keys together. They're asking for the home page. When the client makes a query, they're not getting one key. They're getting hundreds of keys together. Okay, understand this problem correctly. If you have a page that you're trying to load that has a lot of data points, if you shard out, all you're doing is you're spreading those data points all over the place and you have to get them anyway. So instead of just querying one node, you're now going to query 10 nodes. Because the number of requests here are not reducing, they're increasing in fact. So the number of requests to all of these nodes is also going to increase. The single problem has now become a multi-problem because of sharding. So Facebook didn't go for this. Facebook instead went for the idea of replication. When you need to scale to 10x the requirement, you add 9 more servers. Each of those requests can be spread out to 10 different servers, which can answer your queries directly. So Gaurav goes to fetch his homepage. He hits this node, gets a response in 10 milliseconds. When you go to get a homepage, you hit some other node, get the response in 10 milliseconds. If we had sharded out, I would have hit all 10 nodes and you would have hit all 10 nodes, right? So we scaled out in a way which is according to the access pattern that we have. Our requirement was to get pages, aggregate information. Replication makes more sense there than sharding. Now think about the time when you have a massive number of requests. Let's say a celebrity has posted something which has gone viral. Everyone is saying, did you know what they said on Instagram? And everyone is trying to fetch their profile page or they're trying to fetch that particular video. It's also possible that a particular topic has picked up. Maybe SpaceX has sent a new rocket and everyone is talking about rockets suddenly. This heightened activity means more load on your services, which in turn means more load on your caches. So how does Memcache continue serving requests despite high load? So you can scale up the caches, of course, and that is what happens. But at the same time, you have to protect your caches from being bombarded by requests. So you need some sort of rate limiting here. And the way Memcache does this is sliding windows. So each client which is running on the web server keeps a sliding window of the number of requests which are coming in. So these are cache requests. And you can think of this as a queue. So queue has the requests moving till they're picked up by the client. And so you have all these requests coming in here to the server, being sent to the client, and the client eventually is going to start making these requests to the cache nodes. At any point in time, you're going to have a fixed sliding window size. So if a lot of requests flow in here, you're going to start dropping them. Okay, so let's say the size of this queue is 100. The 101th request, which has not been processed yet, is going to be dropped. That's something you can do. In some cases, especially when it comes to caches, there's the idea that you can drop the first request or one of the requests in the head, because those are old anyway. Okay, so it depends on the policy. In this case, Facebook seems to have a sliding window, which means you can't drop them from here, you have to drop them from the back. Now, Facebook's experience here is if they have a large sliding window, then there's a lot of congestion, in the sense a lot of requests have to wait for a long time. The request over here has to wait for a lot of requests to complete first, which is not ideal. Like I said, if the request is very old, the client is going to retry anyway. So why bother? In this case, I'm not talking about this client. I'm talking about your mobile client, which is actually making the request to the web server. So you can drop requests. Don't keep a large sliding window is what Facebook is saying. Also, don't keep a small sliding window, because if you keep a very small sliding window, then the clients keep retrying. Basically, the request comes from a mobile device or a desktop. It reaches your server. If you have a large queue, then this person is happy for a while. Eventually, this becomes old, and then the person makes a retry, which is sad. But if you have a very small window, let's say just 10 requests, then on your initial request itself, you're probably going to drop it. You're going to say, no, I don't have enough space in my queue, which means this client is going to do what? They're going to retry. They're not going to stop watching Instagram. They're going to continue trying. So it's a fine balance. You have to have something which is of suitable size, not too large, not too small, when it comes to caching. The final thing we look into for Memcache is fault tolerance. In case a cache server is being overloaded, despite all of the replication that we have, what can we do? Facebook saw that most of the times that this happens is when a new server is being pulled into the system or a server has been lost. Okay, so there's a lot of heat on that cache. There's a lot of new keys which are moving in. The way to avoid this problem is by using an extra cache. So this is like a spare instance. In case your Memcache server doesn't work, in case you get a fail here, then you just go and query the spare instance. In the case of Facebook, they call it a gutter. Okay, you can think if there's an overflow of water, it goes into the gutter. If there's an overflow of requests, then you can just hit the spare instances. These are around 1% of all nodes on Memcached, and they manage 99% of all failures. Failures are rare. So whatever failures are there, most of them are managed by the gutter instances. The basic idea is these also connect to MySQL instances, just like this Memcached instance, but they are reserved. They are only used in case you have a failure. So the kind of data that they have, the data locality is horrible, right? Any person who has a data failure is going to go and hit the gutter instance. But it is a fault tolerance mechanism, and it's quite good. I mean, it definitely works. For 1% the cost, you get 99% the failure savings. Finally, how is MySQL, this single database, able to serve the entire world for Facebook? A single database server can't do this. We scaled out Memcached these instances. This layer of DB also has to be scaled out. Let's say the Indians have one MySQL server, and the Americans have another one, and the Europeans have another one. How will you keep them in sync? One approach is not to keep them in sync. You have all the data that is being updated here, not being synced here. If that happens, then the Indians and the Americans are going to see different data. So if you have relatives in the US and you want to talk to them on Instagram, no messages. That's not a very good experience. So you want to keep them in sync. Like we said, high consistency is what we want. Very high availability is what we want. Facebook could have used two approaches. One is whenever you're making an update to MySQL, you could have gone and tried to make these updates to the other SQL nodes also. This would require a fan out on the client side, which is a bit extreme. Instead, they went for slightly eventual consistent system, where you have the Indian server take the write, and then it propagates the write operation to these two nodes. Okay, how does it do that? Well, if you have heard of something called change log, okay, you might have heard of transaction log maybe. This is a more popular term. In a transaction log, you have all the operations of a transaction persisted. You have all the commands there. So if you have a create command in a transaction that's written with the details, you have a select command, you have update, you have delete. All of this stuff is written down in a log. If you take this log from the Indian server, copy it here to the US server and execute these commands in sequence, you can guarantee that the copy of the US server will be in sync with the Indian server. That's a very interesting property. Select is just a read operation, so just ignore it. All of these data update commands are put into a change log, and this change log is sent to different parts of the world where you have your MySQL servers, and they replicate these changes internally. Even the Indian server, of course, gets replication from different parts of the world. In MySQL, this is called bin log. The change log is called binary log, and you have all these commands there. Facebook, what it does is really clever. It takes this log file and then sneaks in its own updates, like cache update. So it adds commands to the log file and sends them around. In between, it keeps a server. Okay, this is called Memsql. Memsql is the piece of technology which appends the logs and also propagates them to different parts of the world. Okay, so all of your changes are propagated. One optimization here, the last optimization when it comes to scaling that we'll discuss with scaling Memcache at Facebook is, what do you think is more common? read operations or write operations? When it comes to Memcached, read operations are 1000 times more than write operations. Can you use this to optimize your system? These writes are really rare. So you don't need to have all of these databases serving write operations. You can have one write node for 1000 read nodes, roughly speaking. So in the entire cluster of Facebook, you're going to have just a few write nodes, maybe one in India, one in the US, one in Europe, but you're going to have many, many read nodes. The benefit of this is whenever you're making a write operation, it doesn't fan out. It doesn't have to go and write to hundreds of database servers, a single database server. That's it. Okay, it goes here, and this database server pushes an event to Memsqueal. Memsqueal then manages the eventual propagation of that update across all read and write nodes across systems. In this way, you're able to scale your writes. If you didn't do this, it would result in a thundering herd. All write operations would come and update all the databases. All the caches would need to be updated quickly. No, that's okay. Few write nodes, lots of read nodes. Eventually, everything will get updated because of Memsqueal. So this was scaling Memcached at Facebook. It's one of my favorite papers, and if you have any doubts or comments on this, please let me know in the comments below. If you want to know more about system design, I have a small startup which is trying to build a system design judge at Interview Ready. You can check it out. If you like the video, please hit the like button. I'll see you next time. Bye-bye.